This is AP Calculus AB. Note section 7.8. This is the last section of the chapter. Volumes of solids with known cross-sections. Calculus can not only be used to find the volume of solids created by revolving two-dimensional shapes around an axis, but also the volume of solids formed by cross-sections that are geometric shapes. In this lesson, we will derive the formulas for finding volumes of solids given by their cross-sections, as long as they're squares, isosceles, right triangles, equilateral triangles, and semicircles. We might throw a couple extra in there as well, just to see if you know how to think. Cross-sections that are squares. Here's what that means. Right? Obviously, you know what a square is. Whatever the distance is from function f to g here, that will also be the height, because it's a square. All the dimensions are the same. So this here is going to be a square whose base and height are the same dimension as the distance between f and g. And let's say that distance is 2. And let's say that this square maybe its base and height are 3. And then maybe this next one, maybe its base and height are 4. It's whatevs. Essentially, what we're suggesting is if we want to find the volume of a shape that is made up of an infinite number of cross-sections that are squares, we could find the volume of this figure. How would we do that? As mentioned, the square that we're referring to here, the distance from f and g is the base, and the height is the same difference. So to find the area of this, it's going to be f minus g squared. And it really doesn't matter which one you put first, f or g. Put one before the other, it's going to be positive or negative, but when you square it, it's going to become positive. Find the area of the above square in terms of f and g. Well, as we already know, the area of a square is base times height. And we are suggesting that the base and the height are both f minus g. So the area is going to be f of x minus g of x quantity squared. That's easy enough. If all the cross-sectional areas were added up, the total, to find totals we integrate, would be the volume of the solid pictured. How do we calculate this using calculus and integrals? Well, the volume, we're going to integrate from a to b, where a and b are the boundaries of our closed figure, the x values. We're going to subtract our functions and then square them once we subtracted them, all with mad props to x. What if your cross-sections are isosceles right triangles? So what that means in this context, let's say the distance from here to here is f minus g again. An isosceles right triangle means we have a right angle, and it means that two sides are the same length. Those two sides would have to be the legs. It couldn't be the hypotenuse, it's the longest side. So the height of this triangle is also f minus g. We can see that pictured here. Forgot I had a pointer. Find the area of the triangle above in terms of f and g. Well, the area of a triangle is 1/2 the base times the height. I'm suggesting that our base is f minus g and our height is f minus g. Thusly, I lost control of my things again. I got to exit out and then reopen it. Thousand pardons. F minus g times f minus g is going to be f minus g squared. If you add up all the cross-sectional areas, the total would be the volume of the figure. So this volume is going to be Going to move the half out to the front, integrating from a and b, where a and b are the xi's of the boundaries. And it's the difference of f and g of x squared. So notice the similarity. This is if we have a cross-section that's a square, and this is if we have an isosceles right triangle. What's the difference? The difference is the half. Because an isosceles right triangle is exactly 1/2 of a square. Cross sections at an equilateral triangle. This one's a little more complicated. Okay, it's a lot more complicated. Let me explain where the formula comes from, and then you can just memorize the formula or just always derive this little fella. As we already know, the area of a triangle is 1/2 the base times the height. As we said previously, the base is this distance here, which is the difference of f and g. If it's an equilateral triangle, all these sides are f minus g. To find the area of a triangle, once again, it's half the base times the height. We don't know the height. The height's perpendicular to the base. Special name for the height of a triangle is also an altitude. An altitude goes from a vertex to the opposite side, forming a perpendicular. An equilateral triangle is also equiangular. Each angle is 60. A fact that you no doubt remember from geometry is if you draw an altitude from the vertex angle of an isosceles triangle, it also is a median, meaning it cuts this side in half, which means the length of this side is half f minus g. And it also cuts this vertex angle in half, the whole thing's 60. Each half's going to be 30. Now, why is this so special? Because half of this equilateral triangle is a 30, 60, 90. If opposite 30, so the short leg, is half f minus g, opposite 60, which is the height, is going to be this times the square root of 3. Oh, I lost pointer controls again. Oh, it's so frustrating. Sorry. Notability probably needs updated, and I should probably update it. Or there's a bug. Too soon. Or there's a even sooner. There's a mistake in the programming that's causing this problem. As was said, this fella right here is going to be the square root of 3 times 1/2 f minus g. So, to sum up, the area of this isosceles equilateral triangle is half the base, that's f minus g, times the height, which is the square root of 3 over 2 times the difference of f and g. If we put all this together, the area of this equilateral triangle is going to be square root of 3 over 4 times the difference of f and g squared. Now, how does this compare to the other formulas? Well, this part's identical. We got a square root of 3 over 4 in front for equilateral triangles. So to find the volume, if the cross sections are equilateral triangles, it's square root of 3 over 4. We're integrating from a to b. Those are the xi's of your boundaries where they intersect, of the difference of f of x and g of x, where f of x and g of x are your boundary equations. A lot of similarities between these equations until we get to this little fella. How do you find the area of a semicircle? Well, the area of a semicircle is half the area of a circle. And so that's half of pi r squared. And the radius for this fella is going to be half of the difference of f and g, because the diameter is f minus g. So to find the area of the semicircle, in terms of f and g. Area of the semicircle, we got half pi r squared. The radius we're saying is half the difference of f and g. It's being squared, which means we're going to have half pi. If we square 1/2, we're going to get 1/4. If we square f minus g, we get f minus g squared. This ends up being pi over 8 times the difference of f and g squared. So how do you find the volume of a three-dimensional shape whose cross-sections are semicircles? Well, the volume is going to be pi over 8 times the integral from a to b of the difference of your boundary functions f and g squared. What do you notice about the integral defined formulas for find the volume of solids with certain cross sections? Well, this is the same every time. Let's sum this up. This is the one that we use for semicircles. This is the one we use for equilateral triangles. And these are the two that we use for squares and right isosceles triangles. As mentioned, the difference between all these is the coefficient in front. Square has none. Isosceles right triangle has a half. Equilateral triangle has square root of 3 over 4, and a semicircle has pi over 8. You can memorize those, or you can derive it every time. I would try to memorize it, but know how to derive it in case your memory fails you. R is bounded by f of x and g of x. We've seen these functions before. Find the volume of the solids form whose cross-sections are the shapes indicated. The cross-sections are perpendicular to the x-axis. Now that matters. If they're perpendicular to the y-axis, we have to have our functions in terms of y. So I think most cases they'll be in reference to the x-axis. So equilateral triangles. Well, the volume is going to be square root of 3 over 4. We're integrating from 0 to 2. That's because 0 is this boundary and 2 is this boundary of intersection. We're going to take function minus function. We square it with mad props to x. To figure this out, you would use your calculator. Well, let's use our calculator. Let's assume these are calculator problems because this was meant to be. So you put into y1 parentheses. Well, you could tell you what, might be easiest to do this. Put into y1 sine of pi x. Put into y2 x cubed minus 4x. Put into y3 parentheses y1 minus y2 squared. Then when it comes time to graph this, only have this equal sign on. To turn these equal signs off, put your cursor over this and hit enter, and then the little black thing disappears around it, not racist. And then we got this right here, we want to graph it. And then, you know what, for that matter, let's get nuts. Let's just make this a little bit easier. Let's put in front of this the square root of 3 over 4. So we got the whole thing in there. Everything's accounted for. So we graph this, ask your calculator, second, calculate, integrate, I think it's option 7, and then the lower limit is 0, the upper limit is 2, and I think that you'll find the volume, 3 decimal places, is 4.321. It does say volume, so let's label it as cubic unis. You're going to do that same procedure for all these. Cross sections are semicircles. Well, the volume of a semicircle is pi over 8 and times the integral from 0 to 2 f of x minus g of x, quantity squared dx. Now when it comes time to use your calculator for this, I lost pointer controls again. Son of a mother. It's hard for the language. I haven't had a sugar Pepsi in minutes. It's getting to me. Anyway, comes time to put this in your calculator. All you got to do is go here to square root of 3 over 4 and change it to pi over 8. Ask it to calculate this volume because it's the same functions. You should get 3.918. Once again, you should be using your calculator right now. Pause the video as needed so that you can do these calculations. Cross section for an isosceles right triangle. Well, that's going to be a half times this integral. Use your calculator. You should get 4.989er. That's trucker talk for 9. Cross sections are squares. I'm slurring my speech. It's not what you think. It's not. Stop it. Seriously. Cut it out. Put this into your calculator so there's no coefficient. You should get 9.978. Well, that's interesting. E. Well, nothing prepared us for this. Cross sections are rectangles. We haven't talked about rectangles. Whose height is twice the length of the base. So what would that look like? If we had one of these rectangles, let's say this one's here, not the scale, and the base is f minus g, and the height is twice that, you multiply those together, we're just going to have a coefficient out front of 2. See how that works? Triangle, a right triangle, an isosceles right triangle is a half because it's half the area. This is double because it's twice the height. That is about 19.957 cubic unis. F. Cross sections are rectangles whose height is 1/3 the length of the base. Please pause the video and figure out what that is, what you think it is, and then unpause it. And we're back. This volume here is going to be 1/3 of what it would normally be because the height is 1/3 of the normal height. Square that last one. I lost pointer controls again. Ah! Yeah, I did square. This in your calculator is 3.326. Hopefully I didn't make any mistakes on my calculations. And that wraps her up. Assume that you can use your calculator for all of these unless you're specifically told otherwise. Thank you for stopping by.